Now that you've seen how implicit differentiation works with first derivatives, let's look at how we can use it to find second derivatives. So remember that, just like before, when we find a second derivative, all we're doing is computing the derivative of our first derivative. When we use implicit differentiation to compute a second derivative, oftentimes dy dx is going to appear in our answer. We always want to reduce by replacing the dy dx with the result that you got for dy dx for your first derivative. So if I look at a couple examples here, I think I have 2 examples. On the first one, I'm going to find the second derivative of x squared plus y squared equals 25. Oftentimes the second derivative is symbolized d2y over dx2. So you can see down here with the 2's being squares. So finding the second derivative. So we've already looked at how to use implicit differentiation. Remember, we take the derivative of both sides of the equation, so x squared plus y squared is going to become 2x plus 2y. I always have to tack on the dy dx when I am differentiating my dependent variable equals 0. From here I can now solve for dy dx by subtracting 2x and dividing by 2y. I'm going to do that in one step to leave myself some space for my second derivative. So again, subtracting 2x and dividing by 2y, I get dy dx equals negative 2x over 2y. My 2's reduce, leaving me with just negative x over y. Now, in order to find my second derivative, I'm going to need to be sure and use the quotient rule. So I'm going to let f of x equal x and g of x equal y. F prime of x is then 1 and g prime of x is then dy dx. Squeeze it in there. Okay, so now using that quotient rule on my second derivative, I'm going to take the derivative of the first times the second. So I'll have 1 times y minus the derivative of the second times the first, so x dy dx all over the second squared. So all over y squared. So now, as I mentioned in the beginning, I want to replace that dy dx with negative xy. And I'm going to go ahead and say that dividing by y squared is the same thing as multiplying by 1 over y squared, because I think it's going to look funky to have 2 fractions in there. So that's going to give me y minus x times x over y all over y squared, or all times 1 over y squared. Well, now I can go ahead and I can distribute the 1 over y squared in. I can also multiply my x's, giving me y minus x squared. And so when I distribute the y squared in the denominator, this is a y squared, this is going to be a y cubed. I can add these two together if I get a common denominator of y. So I'm going to go ahead and multiply my first fraction here by y over y, and I get y squared minus x squared all over y cubed. And actually, looking back, I see I have a small mistake. So notice that this was a negative xy, so when I brought it in, I did not keep it negative, so there should have been a negative there, which would have then been negative x times negative x, and this would be plus. And now I can see that based on the original example I was given, or my original problem, x squared plus y squared is equal to 25, according, again, to the example I was given. So I could even replace this here with 25, giving me a final answer of 25 over y cubed. That would be my best, most reduced answer. Let's look at one more example where we use implicit differentiation to find a second derivative. If you would like to pause the video and try finding it on your own first, this would be a great opportunity for you to do that. So finding my second derivative, I first have to find my first derivative, so I'm going to differentiate both sides. I know y squared becomes 2y dy dx. 3x cubed becomes 9x squared minus 2. To get dy dx by itself, I'm going to divide by 2y, and I get dy dx equals 9x squared minus 2 all over 2y. To find my second derivative now, I know I'm going to have to, once again, just like before, use the quotient rule. So I'm going to let f of x be 9x squared minus 2, and g of x be 2y. F prime of x is then 18x, and g prime of x is then 2 dy dx. Plugging my quotient rule in, I get my second derivative is equal to the derivative of the first times the second, so 18x times 2y gives me 36xy, minus the derivative of the second times the first, so minus 2 dy dx times 9x squared minus 2 all over 2y squared, which I'm just going to say is 4y squared. From here I can now substitute this fraction in for dy dx. Just like before, I'm going to multiply by 1 over 4y squared because, again, I think it's kind of funky to have the double fraction. I'm going to slide this over just a little bit so I have a little more room. And I'm going to say that this equals 36xy minus 2 times 9x squared minus 2 all over 2y. My y looks like an x. Times 9x squared minus 2. This whole thing is over 4y squared, which is the same as saying times 1 over 4y squared. So from here, I'm going to go ahead and distribute that in, and I get 36xy all over 4y squared minus 2. I can multiply these, times 9x squared minus 2 squared all over 4y squared times 2y is 8y cubed. Once again, I could get a common denominator so I can combine these. Doing that gives me, so let's see, I'm going to have to multiply this one here by 2y. So 36 times 2 is 72xy squared minus 2 times 9x squared minus 2 squared all over 8y cubed. And unlike the first one, I don't see anything I can substitute back in for. So I'm going to go ahead and leave that as my final answer.